Have you ever really looked at the frost on a window and wondered how it makes those beautiful, intricate tree-like patterns? It just seems so delicate, so natural. But what if I told you the exact same physics is responsible for the brute strength of a massive steel ingot? Yeah, let's dive in and uncover this incredible connection between the fragile and the formidable.
So this is the big question, right? On one hand, you've got these delicate, almost ghostly ice crystals you might see on a cold morning. And on the other, a solid block of industrial metal, the very backbone of our cities. They couldn't look more different. But get this, they share the exact same origin story. To understand how, we've got to start with the absolute basics.
So let's keep it simple at first. We're going to start with a pure element, something like iron, or even just plain old water, right as it starts to freeze.
See, when you've only got one type of atom in the mix, there's no complex chemistry to worry about. It's all about one thing, heat. The whole game of solidification is just about pulling heat out of the liquid, and the final shape it takes depends entirely on how that heat flows away. And the key to understanding how it flows is this idea called the temperature gradient. Now, don't let the fancy name fool you. All it's asking is, as you move from the solid out into the liquid, does it get hotter or colder? That's it. And believe it or not, the answer to that one simple question changes absolutely everything.
So this leads to two totally different outcomes. On the left, if the liquid out front is hotter, that's a positive gradient, any tiny bump that tries to form immediately pokes into that hotter zone and gets melted right back. This keeps the whole front growing in a nice, flat, stable line. But look at the right side. If the liquid ahead is colder, a negative or supercooled gradient, well now any little bump that forms finds itself in the perfect environment to just take off. It becomes unstable, shooting forward and branching out, creating those incredible tree-like shapes we call dendrites.
Okay, so that makes sense for pure stuff, like ice. But what about that steel ingot? Steel isn't pure iron, it's an alloy, a mix of different things. And this, my friends, is where our story gets really interesting.
The moment you start mixing elements, this fascinating process called solute partitioning kicks in. Basically, as an alloy starts to freeze, the solid crystal that's forming is, well, it's kind of picky. It only wants a certain amount of the other atoms. So what does it do? It literally pushes or rejects the extra stuff, the solute, out of its way, back into the liquid that hasn't frozen yet.
Let's walk through a real-world example here with a copper-nickel alloy. You start with a liquid that's a perfect 35% nickel mix. But check this out. The very first bit of solid that forms is actually way richer at 46% nickel. It's greedily pulling extra nickel out of the liquid. So as things keep cooling, the liquid has less and less nickel to give, which means the new solid forming on top is weaker in nickel. The end result is a crystal that isn't uniform at all. It's got a nickel-rich center and nickel-poor edges. We call this a chord structure, and it's happening deep inside that steel ingot.
So, all these rejected atoms, this extra stuff being pushed around, that is the secret ingredient. It's the missing link that connects the dots between a big block of metal and our beautiful crystal forests.
I mean, think about it. Where do all these rejected atoms go? They can't just disappear, right? Nope. They pile up, creating a little atomic traffic jam in the liquid right there at the boundary where all the action is happening.
And this is the truly genius part. What happens when you put salt on an icy road? You lower the freezing point of the water, right? It melts. Well, this pileup of solute atoms does the exact same thing. It acts like a localized, built-in antifreeze, depressing the natural freezing temperature of the liquid in that one specific zone.
This sets up this amazing conflict. You've got the actual temperature of the liquid, which is just doing its thing, cooling down. And then you've got the freezing point, which is no longer a fixed number. It's changing because of that solute pileup. Let's throw this on a graph. It'll make everything crystal clear.
Okay, first up, here's the actual temperature. That line shows a positive gradient. The liquid gets hotter the further away you go from the solid. Now, based on what we learned a minute ago, this should be totally stable. It should give us a perfectly flat surface. No drama here, or so you'd think.
But now, let's overlay the line for the freezing point. And boom, look at that. Because of that solute traffic jam, the freezing point takes a nosedive right there in front of the solid, and you can see it plain as day. There's a region where the actual temperature is now below the freezing temperature.
And that is the big reveal. This special zone is called constitutional supercooling. What a name, right?
But all it really means is that we've chemically created a trap. It's a zone of liquid that is primed and ready to freeze, not because the whole thing is cold, but because we've messed with its local chemistry.
So even with a temperature gradient that should be stable and flat, an alloy can create its very own pocket of instability. Now any tiny bump just has to poke its nose into this supercooled zone, and bam! It's in a place that is just dying to freeze. It shoots forward, it branches out, and a dendrite is born. And that's it. That is how you get a crystal forest growing inside a solid block of steel. Mystery solved. So, we've solved the puzzle of how these things form. But why does this actually matter outside of a science lab? Well, it turns out that learning how to control these crystal forests is absolutely critical for a ton of modern technology.
I mean, think about it. For a steel beam, that internal dendritic structure is its skeleton. It's what gives it strength. But in your phone's battery, those same dendrites are the villain. If they grow uncontrolled while you're fast charging, they can short-circuit the cell and even cause fires. Not good. Then, on the complete flip side, for the flawless silicon needed for computer chips, engineers work incredibly hard to prevent even a single dendrite from ever forming. So whether we want them or not, understanding them is everything.
So that leads to the obvious next question, doesn't it? If these structures can be so helpful one minute and so dangerous the next, how do we get them to do what we want? How in the world do you tame a crystal forest?
Well, it's pretty clever. Engineers use the very principles we just talked about to get control. They can fight back against that supercooling by using a very steep temperature gradient, basically making it too hot for a dendrite to survive. They can also just slow the whole process way down, which gives those rejected atoms time to diffuse and wander away instead of piling up. And of course, it all starts by carefully choosing the elements in the alloy to begin with.
So the next time you see frost on a window, or you lean against a steel beam, remember what's really going on inside. It's not just a simple, solid block of stuff. It's a complex, hidden world, a secret forest of crystals whose shape was decided in the very instant it froze. And it makes you wonder, doesn't it? Now that we understand how to grow these forests on purpose, what incredible new materials, what new technologies are we going to build with them next?